This is problem 2 from worksheet 0328, also known as worksheet number 10, which we did on March 28th. So we have two currents. Actually, there's a bug in the problem statement. They're not both into the page. So these currents are supposed to be equal magnitude, but current 1 here on the left is out of the page, and current 2 here on the right is into the page. This is at x equals minus a along the x-axis. This is at x equals plus a along the x-axis. So this is out of the page, that's into the page. And then we want to evaluate the resulting magnetic field at 3 points. There's the origin, 0, 0. There's point 1 along the x-axis at x equals plus 2a. And then there's point 2 along the y-axis at y equals plus 2a. So, of course, if you just want to read my solution, I put it into slides 2025-0328.pdf, but in the video we can walk through the solution. So these are both infinitely long wires, so we actually need to know the magnetic field due to an infinitely long wire. So if you have a current I out of the page like this, then you can use the right hand rule. Your thumb points in the direction, your right thumb points in the direction of the current, which looking at me is out of the board, and this is actually my right hand. And the fingers of your right hand then curl in the direction of the resulting magnetic field. So the magnetic field is like this. Okay, so we have magnetic field lines that encircle the current. So for this infinitely long wire, it's really easy to use Ampere's law with the symmetry. So we're going to choose an integration path that goes counterclockwise like this. So there's my integration path. And so Ampere's law says a closed line integral of b dot dl equals mu naught times the enclosed current. Okay, so in this case, b dot dl is just b times dl. So this is integral. So b dot product with dl is just b times dl, and dl just equals r d phi, and we'll go around the loop. And actually I think I'm going to make it a lowercase r, because this is going to be it's not really a constant like of the geometry. This is going to be evaluating it at some distance r out from the current, out from the wire. And maybe I'll do this in a different color so it's distinguishable from both the current and the magnetic field and the integration path. Okay, so this is just integral b dot dl is just integral b times dl because they're always parallel to each other, so the cosine theta factor in the dot product is 1, and then this is just the integral of b times r d phi, and we're going all the way around a circle. So then the only thing that's not constant here, because it's a circle, constant radius, the only thing that's not constant is phi. So this is just multiplying by 2 pi. So this is just 2 pi r b. Okay. So then that equals mu naught times I. The enclosed current by this loop is just I. So that gives us that the magnetic field magnitude is mu naught I divided by 2 pi r. If you wanted to give it a direction, you'd say it's this tangential direction. If you want to be kind of fancy with unit vectors, if you had a coordinate system like this, then you would probably define an angle phi up from the x-axis counterclockwise. So then you could say that the b direction is the phi hat direction. You see, phi hat is like this clockwise tangential direction. So if you wanted to, you could say it's in the phi hat direction. I mean, you don't have to do that if you don't want to. Okay, so b is mu naught I over 2 pi r, and it is tangentially counterclockwise if I is out of the page, and it's tangentially clockwise if I is into the page. So let's start with the origin. Actually, the origin is kind of the easiest case to draw. So if we take the contribution from I1, you see this is out of the page. So out of the page means that the magnetic field lines around this current will look like that, and like that, and like that. So over here, it's like that, it's up. And then for I2, this is into the page, so it's going to be clockwise. So that's going to look like that, and like that, and like that, and like that. So these are going to be in the same direction. So at the origin, we're going to have two contributions that both point upward. And if I1 and I2 are the same magnitude, they're going to be the same magnitude magnetic field contributions. So we have the magnetic field at the origin equals mu naught I1 over 2 pi. The distance between this current and this point we're evaluating the field is just A. So that is in the j hat direction. And then we have plus mu naught I2 over 2 pi. Again, this distance is A times j hat. So then that is just, if I1 equals I2 is value I, same magnitudes, just into versus out of the page, then this is mu naught I over pi A, and it's in this plus y direction, so that's plus j hat. Okay, so let's move on then and do evaluate the magnetic field at point P1. Okay, at this point P1, so the current the magnetic field due to current number 2 is going to be clockwise. And again, the magnetic field due to current 1 is going to be counterclockwise, but current 1 is 3 times as far away from P1 as current 2 is. So the contribution from 2 is going to be bigger than the contribution from 1. So if we draw some counterclockwise field lines, they'll look something like this. Actually, here, over here, let's say they'll look like this because they're nearby. And then once we get far away, they're going to be 1/3 as big. So you see this is on the right side here, so it's still up just as this is up, but it's going to be 1/3 as big because we're 3 times as far away from I1. Now the contribution from I2 is going to be clockwise, so it'll be nice and big like that. Okay, so it seems as if the net magnetic field is going to point down here because we have a downward contribution and then we have a smaller upward contribution. So let's work out the numbers for that. So we have the magnetic field at P1 is going to be mu naught I1 over 2 pi times, here's 1, 2, 3a is the distance, and then this is going to be up, so there's j hat, and then we have mu naught I2 over 2 pi a, it's only a far away, and then this is going to be minus j hat. Okay, and then we could, well, okay, so this, here's minus 1 unit, here's plus 1/3 of a unit, so it's going to be minus 2/3 of a unit. So it's going to be minus 2/3 of mu naught. Okay, this is for I1, again, I2 equals I1 equals I, same magnitude. So there's mu naught I over 2 pi a. 2/3 of that, so the 2 cancels and we get a 3. Oh, there's j hat. So this equals minus mu naught I over 3 pi a j hat. Okay, so that's not so bad. Then next we're going to move on and evaluate the magnetic field at P2, which is a little trickier. It has some trickier vector arithmetic. Okay, now at this point P2, to get from current 1 up to P2, we go 1 unit to the right and 2 units up. And to get from I2 up to P2, we go 1 unit to the left and 2 units up. And this contribution from I1 is going to be, again, it's going to be counterclockwise and perpendicular to this radius vector. So the tangent to this circle is going to be perpendicular to the radius vector of this circle. So that's going to point, let me erase this coordinate here. That's going to point this way. So there's a right angle. And then the contribution from current 2 over here at P2 is going to be clockwise and tangential. So that's going to be, again, perpendicular to this radial vector. So that's like that. And then so then clearly when you add these two vectors, the horizontal parts will cancel and the vertical parts will add once we impose the condition that the two currents are the same magnitude. So we want to evaluate that vertical component. One thing you could notice is if you, let's write in some kind of a definition of an angle. So let's call this angle phi. Then, for one thing, the sine of that angle phi, which is between the radial vector and the vertical there, must be, so it's opposite over hypotenuse. So that must be A over, see this is 2 and that's 1, so 2 squared is 4 plus 1 is 5. That's A over A root 5, which is 1 over root 5. So how does that relate to what we really want to know is the angle between this thing and we want to know the angle between this tangent vector and the horizontal. And the sine of that angle will give us the y component here. I claim this is the same angle phi because this magenta arrow is perpendicular to this white line. This angle phi is from the vertical to this white line. This angle phi is from the horizontal to this magenta line. So I think that makes sense. So this white dotted line is perpendicular to this magenta arrow. This y-axis is perpendicular to this translated x-axis. So I think that's okay. So that is phi. So then the y component is just the magnitude of this thing times sine of phi. The y component of this is the same as the y component of this. I sometimes write this out with unit vectors, but this is, I think, just fine to do it with angles. So let's work that out. So then we have the magnetic field at P2. It's going to be in the plus j hat direction. We know that because the x components are going to cancel and the y components will add. Let's just do one of them and multiply by 2. So let's just do this magenta arrow on the right and we'll multiply it by 2, and that gets us the complete answer, which would account for including the green one on the left also. How big is that? This is going to be mu naught I over 2 pi. How long is this radius vector between this current and this point P2 where we want to evaluate the field? Again, this is a squared plus the quantity 2a squared. A squared plus 2a squared square root of is a root 5. So that is a root 5 for the distance here. And now we want to multiply by the sine of this angle phi. And the sine of that angle phi is 1 over root 5. So I'll just erase that and write 1 over root 5. So that factor corresponds to this thing is the sine of phi. So then our final answer is, so root 5 times root 5 is 5. This 2 cancels this 2. So this is mu naught I over 5 pi a times j hat. Does that make sense? Mu naught I, 5 downstairs, pi a has the right units, mu naught I over blah blah r. Yeah, I think that looks good. Let's compare to what I got earlier. Mu naught I, j hat over 5 pi a. Good. Okay, so the tricky part there was basically adding the vectors. I mean, you see, you could translate a copy of this green vector over here, and then when you add them, you get this vector. So that makes sense. It points up.